This lecture has three parts. The first is reviewing some more details about complex numbers. Then we start playing around with powers of complex numbers. This is our introduction to the symbol n, which stands for the number of frequency bins, if you're going to look this up outside of the course. The v in this becomes the inverse ifft matrix, which is in about the middle of the course. So we're beginning to introduce concepts that have fruit in the future. K is a counter, pi, and then the third part is playing with the equation of an ideal sinusoid. And we have to understand the amplitude, angular frequency. You should have studied a bit of this in physics. The first major concept is a pattern doesn't have to repeat in time. A pattern can be just one spike that exists only for a moment, has infinite amplitude. Or a pattern can be a step, which occurs at a certain point in time that's very clear and transitions from one amplitude to another. Any pattern can be in turn modeled as a series of infinite sinusoids. And you've probably had some experience with Taylor series. The most interesting thing here is that this ... can be thought of as just becoming more and more accurate. When we are raising an angle to a power, we have to remember to subtract 2 pi off of it. It becomes a finite thing. It doesn't blow up to an infinity. So, in a true sense, this series expansion is just making the cosine more accurate. This is all stuff we've seen before. This is the new concept that we're going to explore more. We're introducing it here. Basically, cosine stands for the real world, and we're saying that it can be thought of as two things in the complex world. Here we see the first indication of n. Our goal is to solve for z. So what we do is we take v and we chop it up into a circle. We think of it as a circle, and we chop it up into n pizza slices. And what we end up with is this visualization of it. So here n is 4 pizza slices. If we increase the number of n's, we just have more pizza slices. Here's n equals 3 in this particular example. So it's good to start visualizing n and v by looking at this polar plot. We've established above that any pattern can be thought of as a group of sinusoids added together. The question is, what sinusoid? We have two types of sinusoids. They're both periodic, they're both polar, but one's even and one's odd. Cosine is even symmetry. This means that an angle is 0, its entire amplitude lies in the real world. Sine puts the entire amplitude in the imaginary world, which means in the real world it's 0. So it's a little bit more complicated, and we tend to focus on cosine in this course. So now we're going to focus on a single sinusoid that might make up our pattern and defining it. And these are all the new symbols that are introduced in this lecture. X is the real part of a complex number. Remember, the complex number is the symbol z. The amplitude is the letter A. Now this one's unusual. Capital omega, it's a Greek symbol, is the angular frequency in radians per second. And this is our starting point, not frequency. Frequency is a derivative of the angular frequency. Period is a derivative of the frequency, and ultimately the angular frequency. So these two basically follow from omega. T is a matrix that gives us a sequence of numbers that form a sinusoid. So T becomes the horizontal axis, and then x of t becomes the dependent or vertical axis. Phi then is an offset. So it moves our peak this direction if we're shifting earlier in time, phase shift earlier in time, and phi is positive if we're shifting later in time. So phi is negative if we're shifting earlier, positive if we're shifting later, which seems obvious, but it doesn't sit well in my brain. I have to chant that to myself. So our immediate goal is to understand what these symbols mean, and the ultimate goal is to find sinusoids in random data. So we're actually looking for perfection in the data itself, and this is the perfection we're looking for. Now A itself is the magnitude, which is in this case 2, from 0 to 2. It shifts from 2 to minus 2 to 2 to minus 2, and everywhere in between. These are the formulas that relate the angular frequency to hertz and to period. Now, this example is confusing. What we're trying to do is translate what we observe into a sinusoid. It's hard to observe the actual peak A, the magnitude A. We can pinpoint a spot before A and measure the distance between those two spots. But finding an absolute value of A, finding that inflection where the slope changes in the math, is very difficult in the actual data itself. So this is the kind of information we gather looking at a screen, looking for a possible sinusoid in our data. It's hard to determine where 0 is or what the phase is relative to some other sinusoid. Our goal is to avoid all of this when we actually do the FFT algorithm. So basically you take this one problem, split it up into 3 problems, and this is all the math through it. But again, you can see we do this math thinking in terms of polar notation.